video, we're going to take a look at constructing or running a one-prop Z test for a population proportion. So I play a lot of Ultimate Frisbee, and sometimes when we play, we will flip to see who gets on what team. And we kind of assume that it's pretty fair between heads and tails, but if you kind of look at this, it's not very flat, and most of the plastic is on this side, so I always kind of wonder, is it really 50-50? I kind of feel like if this is heads and this is tails, it's going to land up tails up most of the time. Just because of the way it's shaped. So how we're going to run this is we're going to flip this a whole bunch of times, we're going to see what happens, and we're going to assume that it's actually 50-50 and just kind of see what the observations are. How far away is it from that 50-50 assumption? So we're going to go ahead and flip this a bunch of times. Count them up and see what happens. So we've collected all our data here, and after flipping that frisbee by about 60 times, we see that we had heads come up 36 times and tails come up 24 times. So it looks like my assumption might have been wrong about it being tails more often, but we're going to go ahead and run a significance test and see if this difference is big enough to have not just been random variability. So before we run our significance test, I just want to recap that we have a 4-step process here. And the first step is to state your parameters and define your null and alternate hypothesis. Then state the procedure and check the conditions that they're met. Then step 3, you're going to calculate your p-value, and step 4, interpret that p-value in context and either reject or fail to reject your null hypothesis. Now let's talk about that calculation of the p-value. To do that, what you're going to need to do is find what's called a test statistic. And a test statistic for proportion or for means is going to be equal to the statistic minus the parameter from your null hypothesis divided by the standard deviation. So for proportions, what we're going to be looking for is a z-score, since we're using the z-curve, and that's going to be equal to p hat minus p naught divided by the square root of p times 1 minus p over n, all in the square root. And the p here that we're going to use is p0 and p0 because we have an idea about the population. So let's go ahead and run this process. So first thing we're going to do is we're going to state what our question of interest is, state our hypotheses, state what type of procedure we're going to run. So our question of interest here is we're going to test whether flipping a frisbee is quote-unquote fair, whether it's really a 50-50 chance of getting heads versus tails. So our parameter of interest is going to be a proportion, and we defined it as, I was looking at tails first, so I'm going to say that p is equal to the proportion of the flips that are tails. And our null hypothesis, we are assuming that these are going to happen with the same likelihood. So our proportion should be 0.5. And since I'm testing whether or not it's fair, I'm going to have an alternate hypothesis that p is not equal to 0.5. Even though I had kind of a suspicion about one way or the other, I just want to see whether it's 0.5 or not. I want to find evidence against the idea that it's a 0.5 probability. So first off, we're going to say that we are running a one-prop Z test. And you should throw your alpha level in there too. And since we weren't given an alpha level, we're just going to go ahead and choose that 0.05 will be our alpha level. Now that we've stated what we are going to do, we need to show that our conditions are all met. So we need randomness. And we weren't taking exactly a random sample. This is really more of a randomized experiment. And I think we can assume that each flip was a random outcome of some sort of natural phenomenon. So I think we have randomness is set. We need independence. And now if we were sampling without replacement, like from a population, we would need to show that n is greater than or equal to 10n, but we're not really sampling from a population. What we need is that each flip should have no influence on each other flip. So I think we can safely assume that we have independence. And finally we need normality. So we need NP and N1 minus P to be greater than 10. Well, N times P, how many successes did we have? Well, we had 24 that were tails. That's greater than or equal to 10, so that's met. And also N1 minus P, how many failures did we have? We had 36 that came up heads, and that's greater than or equal to 10 as well. So all three of the conditions are met to run a one proportion z-test. Next thing we'll do is calculate our test statistic, which is our p hat. Well, we need to know what our p hat is, I guess. Alright, so we had 24 successes out of 60 trials, so that's giving us a p hat of 0.4. So it's clearly different from our parameter that we had in our null hypothesis of 0.5, but is it different enough to not have just been random chance? So we're going to divide that by our standard deviation, and since we're basing this on our null hypothesis, that is 0.5, we're going to use that here. 0.5 times 1 minus 0.5 is just 0.5, divided by 60, and let's see what that gives us as a test statistic. So that gives us a test statistic of negative 1.55. So in terms of standard deviations, that seems to be a fair amount away from our null hypothesis. So we need to calculate exactly how far away that is. So if you have an inspire, then that's what we're going to use. So if you go into the menu and statistics, distributions, we need normal CDF, because what we have is we have a normal curve, and somewhere over here we have negative 1.55, and that's our z-score. The p-value is going to be the area to the left, and because this was a not equal to alternate hypothesis, this is a two-tailed, so we also have a tail to the right that we'll need to check. So if we go from negative infinity to our z-score, negative 1.55, leave those the same, and we have one tail is 0.06, and that means the other tail is also 0.06. So we have a p-value that is equal to 0.12. Since our alpha level is 0.05, we don't have enough statistical evidence to claim that the flipping the frisbee is really unfair. We don't have enough evidence that it wasn't just chance. There's a 12% chance we would observe something this extreme. So since p is greater than alpha, we don't have enough evidence So since p is greater than alpha, we don't have enough evidence to reject the null hypothesis that flipping the frisbee is fair. That is a probability of 0.5 to get heads or tails. So that right there, that is a one prop z test. You start out by collecting your data to answer some kind of question of interest. Then you go ahead and say what that question of interest is, state your parameter, state your null and alternate hypothesis, say what you're going to do, show that all the conditions are met, calculate that test statistic, and then interpret what that p-value is. Now there's a way that the Inspire can save you some of this time, at least with this calculation stuff. So let me show you real quick how to do that. If you go into your menu and statistics, and just at the very bottom there you got stat test, so click stat test, and we're going to be running a one prop z test, so that's number 5. It asks you for your null hypothesis. Ours was 0.5. The number of successes we had was 24. The number of trials we had was 60. And here you've got an option, if you bring that drop down, to pick one of your alternate hypothesis. So ours was not equal to. That's what we're going to choose. Enter there, and we have our z-score, we have our p-value, we have our 0.4, we have our 60. So if you're doing it this way, then you need to report all those things, your z-score, p-value, p-hat, and your n, to be able to get full credit.